Hello everyone, welcome to EEEE lecture number 4. So let us start with DC circuit analysis. So what do you mean by DC circuit analysis? It means that we need to determine the current flowing through, or we need to determine the voltage across every element in the circuit. Alright, so the bigger picture is we will learn the techniques to carry out the DC circuit analysis. Alright, so after few lectures, whenever we are given a circuit, we will be in a position to apply any of our DC circuit analysis techniques to solve that particular problem. That means one particular problem can be solved by different techniques. Okay, so in this case, in this direction, let us first start with Kirchhoff's law. So in Kirchhoff's law, there are two laws in there. We have KCl, that is Kirchhoff's current law, and we have KVL, which is Kirchhoff's voltage law. KCl is associated with loop or mesh analysis, and KVL is associated with nodal analysis. Okay, so we have both of them in your syllabus. Now, let us understand before going to the actual KCl and KVL, let us understand few terminology related to this direction. So, what is a circuit? A circuit is an interconnection of circuit elements, passive elements, and energy sources such that the energy flows between the elements. All right. So, a circuit can consist of a voltage source. It can consist of a resistor. It can also consist of a current source. All right. So, this is a simple example of a circuit. So, this is resistor R1. This voltage V1, current source I1, and this resistor R2. So, this is my circuit. So it's an interconnection of circuit elements, passive elements, and energy sources. So here V1 and I1 are my energy sources, such that the energy flows between the element. Alright. So what we need to do? We need to analyze the circuit by formulating network equations that are governed by Kirchhoff's law. And in Kirchhoff's law we have either it can be governed by KCL or it will be governed by KVL. Alright. So let's proceed forward. And these laws can be intelligently employed to formulate the minimum number of independent equations. Alright, so that is where our intelligence comes into picture. So whenever we analyze the circuit, we have to analyze in such a way that whatever laws we are studying related to Kirchhoff's KCL or KVL, we have to intelligently employ that, and then we have to formulate minimum number of independent equations to solve a circuit element. Alright, in this juncture, we will understand what is a node or a junction. Okay, a point of connection of two or more circuit elements is called as a node. Okay, so let's say that we have two elements, let's say two resistors connected in a circuit. Let's say this is a voltage source and this connected like this. So tell me what is a node over here. So node will be here, this way. So this is my node, a point of connection of two or more circuit elements. So it's a point of connection of two or more circuit elements. Alright. A node is a point where two or more branches are connected together. That's the alternate definition of a node. Okay. This is also called as a node, but this we call it as a reference node because this is normally connected to the ground. Okay. This is reference node. Got it? Node or a junction. Now let us go back down. Now we'll understand what is a loop. Any closed path through the circuit in which no node is encountered more than once. Alright, so let's say you have a circuit like this. This is my voltage source. I have my resistor. Okay, let me redraw this part. So here I have another voltage source. So identify the loops in this. So here is one node over here. So let me draw the loops in red color. So this is loop number 1 and this is loop number 2. So any closed path through the circuit in which no node is encountered more than once. So here there is another node. So no node is encountered more than once over here. That means it is a loop. Okay, and any closed circuit it is. Alright, I hope you are understanding. Now a branch is a path between two nodes. Okay, so let's say you have two nodes here, node A and B, and there are many things connected to it. Let's say you have connected a voltage source, current source, a resistance, and so on and so forth. So these are my two nodes A and B, and these are my branch. This is my branch. Okay, these are my branches. So a part of the circuit containing one circuit element and nodes on both the sides is called as a branch. All right. So this is also a node. Okay, so these are all our branches. All right. Now ground or reference node. So this is useful to have one reference. It is useful to have one reference node such that all the voltages are expressed with respect to reference ground. So ground is represented as follows by this symbol or by this symbol. All right. Now let us understand. Take an example and try to understand whatever terminology we have tried to learn over here. All right. So first, let us identify the reference node. Okay. So this node is my reference node where one or more elements are connected. So this is my reference node. Okay, is this a node? Yes, two or more elements are connected. So let us call it this as B, this is also a node. Now this node and this node are one and the same. So I have clubbed them together. So they are clubbed together. So these 3 points are one and the same point only. Similarly below, these are all same points. Okay, so we have clubbed them together. Now let us see how many nodes are there over here. So excluding the reference node, so we can call this reference node at point C. So how many nodes are there? Let us write it down. There are number of nodes are 2, A and B. Okay, node A and B excluding the reference node. Now how many reference node are there? Reference node is 1, that is C. All right. And how many branches are there? So the branches, let us count in red color. So this is one branch between two nodes. Another branch, 1, 2, 3, 4 and 5. So total there are 5 branches. Okay. So branches are this 10 volt voltage source, 5 ohm resistor, 2 ohm resistor, 3 ohm resistor and 2 ampere current source. All right. Okay. So we have identified the nodes, reference node and branches. Okay, so this is example number 1. It is helpful to understand what are these quantities, that is node, reference node, branches, loop. Now let us take example number 2. So here we'll identify loops, branches and nodes. All right. So first let us mark nodes. So this is my node A. Okay, 2 or more elements are connected. This is my node B. This is also same. So this node is also B, and this is my reference node, which we'll call it as a C. This is my reference node. All right. Now, how do we define a loop over here? So this is a closed circuit part. Okay. So this is one loop. Let me mark it with red color. This is one loop. Loop number 1. Okay. Do we have any other loop over here? Yes. Yeah. This is another loop. Okay, this is number 2, and the third loop is over here, number 3. So there are 3 loops in total. So let me write how many loops are there? 3 loops. And how many nodes are there? A, B and C, including the reference node. So there are 3 nodes. And how many branches are there? Let us write it down. So this is 1, 2, this 10 volt voltage source, 5 ohm, then this 2 ohm, 3 ohm and 2 ohm. So there are actually 5 branches. So let me identify these loops. So loop number 1 is between, we can write it down, A, B, C, A via 2 ohm resistor. So it is A, B, C, A via 2 ohm resistor. Now loop number 2 is B and C via let's say B and C via 3 ohm resistor. Okay, and loop 3 is between B and C via 2 ampere current source. BC via 2 ampere current source. All right. Now there is another formula over here, that is B is equal to L plus N minus 1. Now B is number of branches, so these are 5 over here. L, what is L over here? L is nothing but number of loops. So number of loops are 3 over here. N is node. A number of nodes are 3 minus 1. So as you can see, this equation is getting satisfied. Alright, if we want to find number of branches, we can do that easily over here. Okay, is this clear? So these are my 3 loops. Let me mark them with colors. So this is my first loop, yellow color. So this is my loop. Then next loop is with green color, this one. And next is with blue. Yeah, this one. So these are my 3 loops. Got it? Okay, let's go to another example. Now let us take this one more example, and let us try to define the number of nodes, branches, loops. Okay, so let me start. So how many branches are there? I mean, how many nodes? So we have defined the nodes over here. This is a node. This is a node. This is not a node because no circuit element is connected extra. This is a node. This is my reference node. Let's consider. Ground node is a reference node. This is a node. This is a node. So number of nodes are, this is 1, 2, 3, 4, 5, 6. So there are 6 nodes in the circuit. Alright. How many loops are there? We can identify the loops as follows. This is loop number 1, loop number 2, loop number 3, and loop number 4. So basically there are 4 loops. Now let us identify the number of branches. So this is one branch, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 9 branches. Got it? So this is the way we can identify a node, loop, or a branch in an electrical network. I hope by now it is clear. Okay. So yeah, we have written this formula before, circuit element network, where B is the branches, N is the number of nodes, L is loops. So this equation will help us greatly, in studying the various voltages and currents in an electrical circuit. Okay, so let us start with the first law. So please write it down, Kirchhoff's current law, or call it as KCL, Kirchhoff's current law, also called as KCL. So what does KCL says? It says that algebraic sum of all the currents entering or leaving a node is equal to 0. Okay, I'll explain that with an example. So let me see that this is a node and there are some incoming currents. So what are the incoming currents over here? Incoming currents are flowing into the node. So we have 2 ampere, 3 ampere, then we have another 2 ampere, and then we have 7 ampere. So these are all incoming currents. Then outgoing currents are I2 and 4 ampere. Got it? So here what it says is algebraic sum of all the currents entering or leaving a node is 0. So we'll add all the terms. So incoming currents will be positive, outgoing currents will be negative. So 3 ampere plus 2 plus 3 plus 7 and minus I2 minus 4 is equal to 0. So this gives us I2 as 10 ampere. Okay. So that is what algebraic sum of all incoming currents and outgoing currents is equal to 0. Algebraic sum of the current leaving a node is equal to the algebraic sum of the current entering a node. So we can rewrite this as follows. Incoming currents are 3, 2, 2, 7. So that is equal to outgoing currents, that is I2 plus 4. Okay, so this is the second statement. Still we are getting the same answer. I2 is 10 ampere. Okay, so this is the first statement. This is the first statement. This is the second statement. So both are actually one and the same only. It's the way of interpreting it. Okay, so got it? KCL. Alright, let us consider this example again. So I have a node O. So we'll apply KCL. So what are the incoming currents? I1, I3 and I5. So I1 plus I3 plus I5. And what are the outgoing currents? I2 and I4. So minus I2 minus I4 is equal to 0. Or we can call it I1 plus I3 plus I5 is equal to I2 plus I4. That is, incoming currents is equal to outgoing currents. That is my Kirchhoff's current law. Okay, got it? Fine. Now let us analyze let us see this KCl depends upon, the nodal analysis depends upon KCl. So first of all, we'll go through the steps. So the first step is define a reference or a ground node. Then define a variable to indicate the voltage at other nodes. Now, instead of reading it out, let us apply them. So this is an example. Of nodal analysis, then using KCl to find the current I1. So current I1 is the current flowing through 4 ohm resistance and the power absorbed by 6 ohm resistance. Okay, here is written power formula. Power in DC is given by V into I, or V square by R, or I square into R. Alright, all are one and the same. Now let us focus our attention over here. So what does the nodal analysis say? Nodal analysis says we need to define a ground node where maximum number of connections are cut. So connections are made. So here is my reference node. Let me mark in yellow color. So this is my reference node. All are one and the same point. Okay. So after defining the reference node, define the variables to indicate the voltages at other nodes. So here, the above node over here, let me highlight it. This node over here, all the nodes are one and the same thing. Got it? Okay, let me reconnect my tab over here once. Okay, yeah, got it. So all the nodes connected over here. Okay, it's responding. So here I have this node, all are one and the same point. Okay, so I'll define a variable over here as node number 1, and I call this voltage as V1. Okay, so what I did is I've defined a variable to indicate the voltage at the other nodes. Now apply KCl to each node. Now here we have only one node, so we'll apply KCl to that particular node. Okay, and associated with that particular node, so we'll apply KCl and we'll write, let me take blue color, so KCl at node 1. Alright, now here 6 ampere is outgoing current, I1 is also outgoing. We have to define the direction of current leaving the this node. So always assume leaving current, okay, leaving the node. Alright, this is I2 and let us say that this is I3. Got it? So now we'll define this as what are the incoming currents over here? 6 outgoing currents. Outgoing currents are 6, I2, I1 and I3. So let me write 6 plus I1 plus I2 plus I3, and what that is equal to outgoing current, which is incoming current, which is 4 ampere. So this is equal to 4. Now 6. What is I1? Now I1 will be, let me rewrite this and explain this concept again. Let's say you have this scenario where we have V1 with V2 with respect to ground, voltage V2 across the resistor with respect to ground. This resistor R1. So how do we define the current through this resistor? So current through this resistor will be V2 minus 0 upon R1. Okay. So here IR1 will be V2 upon R1. Got this concept? So this is basically a Ohm's law. So here also I1 can be written as V1 minus 0 upon 4. So it's actually V1 upon 4. Similarly, I2 will be V1 upon 6 and I3 will be V1 upon 12 is equal to 4. Now, you can solve this further and check it out. The answer will come out to be V1 is minus 4 volt. So please check out this answer. Please check this answer. Alright. So in the meanwhile, since some people are checking, okay, you got the answer, right? Okay, good, great. Now I don't want V1, I want actually I1. So what will be I1? I1 will be V1 upon 4, and V1 is how much? Minus 4 upon 4, that will be minus 1 ampere, and the direction is down. Now if I want to write this as plus, I can write I1 is equal to 1 ampere, direction will be above, direction will be opposite. Alright. Now I also want to find the power through 6 ohm resistance. So power through 6 ohm resistance will be let's say V square by R, right? So I can say V1 square divided by 6 ohm resistance. okay, because this is the resistance I want to find the power, right? So P6 will be V1 square divided by R. And what is V1 square? V1 square is 16 divided by 6 watts. So this is my power consumed by 6 ohm resistance. Okay. So we can check this out quickly in LT Spice. I hope you have followed this a simple example of finding current I1 and power absorbed by 6 ohm resistance using nodal analysis. Alright, now let us check this out in LT Spice. Let me minimize this part and let me adjust the window of LT Spice. I have shared the links of LT Spice download link. So you can download this software and try to, simulate the circuits which we do in the class. Alright, so this is my circuit. So let me go to the library and take current. Okay, here I'll place it over here. Then I require resistors, two of them, 1, 2, and I require one more resistor over here. So let me add one more resistor over here. Then I require another current source. So I'll go to component and type current. I need to rotate the direction, so control R I'll press. Alright, so my circuit elements are ready. Now I have to connect all of them with a wire. So let me use a wire and connect all of them. Yeah, that's it. And then I'll connect the remaining elements with the wire, circuit elements. So the circuit elements are 3 resistors and 2 current sources. So wherever there are more current sources involved, it's easier to apply nodal analysis using KCl equations. Now I require a ground also, so I'll add a ground over here so that the circuit is complete. And LT Spice, it's a mandate to add a ground. Now this value is how much? 6 ampere. So I'll right click, add 6. This is 4 ohm. This will be 6. This current source is 4 ampere and this resistance is 12. Alright, and I'll define here over here V1. Let us see what is the value of V1 after simulating. In our case, we got the value of V1 as -4. So let us see whether we get this here or no. So I'll go to simulate, run, DC operating point, click on OK. So as you can see, V1 voltage is -4 volt. Okay, so that's the voltage we get, and it is matching with this value over here which we got. Okay, and also we need to find the power through 6 ohm resistance. So to find the power, just bring your cursor near your 6 ohm resistance. So do you see bottom over here, dissipation written, bottom of the window, dissipation written 2.6667, right? Watts. So watts. So here 16 by 6 will be 2.6667. So that is answer is also matching now very clearly. Got it? So in this way, using LT Spice, we can simulate any circuit, any simulation, any linear circuit very easily. All right. So I hope this concept is clear now. So let us move on to the next one now. Let me maximize this part. Okay. Now we go to Kirchhoff's voltage law. It states that algebraic sum of all the drops or gains of voltages around any closed path circuit is equal to 0. So we'll go to an example and let us find that. Okay, so we need to find VBD in this closed loop circuit. Okay, so here I have two voltage sources and 3 resistors. It's a loop, all right, and let me define this loop current as I. All right, now I'll apply the KVL to the loop B. I'll define your node as C, B, C, D, B. So what do I get? I'll start from here. See, I'm starting from here. Okay, I'm starting from here, and then I'm going till here for here. Then this 12 volt and this 30 ohm resistance. So I'm starting from here. We are going from negative to positive. So we'll write 6, and then current direction. If it is the same direction of current, then it will be I mean, here we have defined plus minus, let's say. So it's going from positive to negative potential. So current will be negative. So minus 10I minus 20. Here also we define plus minus. So minus 20I. Then we are going from positive to negative. So there will be a fall in potential. So minus 12 and minus 30I is equal to 0. Okay. So here if we calculate, minus 60I is equal to 6. So current is minus zero point 0.1 ampere. So that's the current which I am getting. Now I need to find the voltage VBD. Now how to find the voltage VBD? Let me remove this loop. Okay. Now VBD, if I want to find VBD, I'll always start with the lower value V, the reference node D, and you go above. Okay. Now the direction in which we are going was this way. Okay, from below to above, and the current direction, if the current direction and this loop direction above loop, what we have drawn over here, okay, this is wrong, this should be above. If the current direction and this direction, the green color arrow direction are same, then the current will be negative. If the directions are opposite, then the current will be positive. So what I mean is your VBD will be, you go from down, it's a rise in potential, so it will be 12, and then we'll go to 20 ohm resistance. Then this current, I mean this direction of green color arrow and this direction of current I are opposite, so it will be plus 20I. And how much is I? I value is around minus zero point 0.1. So this number will be 12 um, minus 2. Okay, so that will be 10 volt. So VBD voltage will be 10 volt. Alright, so now how do we apply first statement? Algebraic sum of all the drops or gains of a voltage around the closed part is equal to 0. Okay, so what it means is, if I have this network and I define the current in the loop as I, this is the voltage plus minus. Here we have VR1 plus minus. Here we have VR2. Voltage drop across R1, voltage drop across R2. And now if we apply KVL, what it says is the algebraic sum of all the gains or voltage drops are equal to 0. So here we are going from here. Okay, let me maximize. We are going from here and then we'll go back over here. Okay, so we are going with the direction as outer loop as this way. This way. Okay, so here we get there is a rise in potential. So here we get Vs. Here there is a fall in potential. So minus VR1. Here is again is a fall in potential from positive to negative. Here it is minus VR2 is equal to 0. Alright, so that's what it meaning. The algebraic sum of all the gains or the voltage drops are equal to 0. So that's the first statement of KVL. Then the second statement is algebraic sum of all the drops of voltages is equal to algebraic sum of all the gains of voltages across the closed part. So what it means is all the gains is equal to all the drops. So addition. So this and this is the first same thing. Okay, this comes from first statement and this came from second statement of KVL. Okay, I repeat, algebraic sum of all the drops or gains of voltages around the closed path is equal to 0, or algebraic sum of all the drops of voltages is equal to algebraic sum of all the gains of voltages around the closed path loop. Alright, so these are the first and the second statement. Okay, so if you're confused about the sign, just follow this carefully. A rise in potential is same as voltage, can be assumed as positive, while a fall in potential is assumed as negative. Now please consider the first case over here. So first case, we are going from here to here, okay, from left to right. So we are having a fall in potential, okay, and on the right hand side we are going from minus to plus. So we are having rise in potential. Alright, if we have a resistance and if the current is flowing in the same direction of plus minus, so here again there will be a fall in potential, and here if it is minus plus, then it will be a rise in potential. Got it? So current will always flow from positive to negative. Remember that. So these conventions are very, very important. Now let us solve numerical number 1. Find the potential difference between X and Y in the circuit shown below. So these are my nodes X and Y, and we need to find the potential difference between these 2 points. Alright. So don't be afraid, it's a simple circuit only. Now let's apply. Here it's a circuit, resistive circuit consisting of a voltage source and 2 resistance. So we can easily apply, here we can easily apply a simple Ohm's law, right? So how can we apply Ohm's law? Here. So current direction will be negative to positive, let's say. So this is my current I, and over here, how will I define my current direction? Yes. So like this way. Okay. If I have a circuit like this, how will I define my current now? Going from negative to positive. Got it? So this will be considered as a positive current. So this is I2. So here also I can find I1 and I2 very easily. So how much is I1 now? I1 will be 2 volt divided by 2 ohm plus 3 ohm resistance. Okay. I is V by R. Okay. So this will be 2 by 5 ampere. Similarly here I2 will be 4 volt divided by 3 ohm plus 5 ohm. So that will be 4 by 8. That will be zero point 0.5 ampere. So I1 and I2 we have found out, and now we have to apply the KVL from the part X to Y. Okay. So let me slightly minimize this. So we will apply KVL and around this loop. So we'll go from Y and then we'll move on to X. So actually we are going in this direction. Okay, going in this direction and going in this direction. Now if the current direction is also the same, then it is negative. If the current direction is opposite to this green arrows, then it is positive. Voltage drop is considered to be positive. So we'll go from here. So what do we get? If we start from here, Vx, that will be Vx. Then this current and this direction is same. So what do we write over there? Yeah. So what do we write? The current direction and this direction is same. Actually, we should start with Vy. Okay, we are starting from Vy. So Vy, then this direction and this direction are not same. So my plus 3I2. All right. Then we are going from plus to minus. We are going from y to x. So it's fine. It's fine. We can find from y to x also. So we are going from bottom. We are moving up, and then we are moving down. We are going from plus to minus. So we are going minus 4. Then this current direction and this direction is same. So minus 3I1 minus Vy is equal to 0. Got it? Now from here we can easily find what is Vx minus Vy. So Vx minus Vy will be how much? It will be, we have, let's say we have over here Vy minus Vx first. That will be equal to minus 3I2 plus 4 plus 3I1. So here Vx minus Vy will be 3I2 minus 4 minus 3I1. Got it? So Vx minus Vy will be, I2 is how much? 0.5. So 3 into 0.5 minus 4 minus 3I1. I1 is 2 by 5. Got it? So you can check it out, and your Vx minus Vy voltage will come out to be minus 3.7 volt. Okay, so this is the way we can find by applying simple KVL, the voltage difference between, potential difference between terminals A and B, X and Y. Okay, so that is minus 3.7 volt. Now let us check it out this in LT Spice, and that this is the last numerical for the day, for this lecture. Okay, so let me create a new schematic. Let me minimize this. Okay, Now let me recreate the circuit. So I have voltage source, inverted voltage source. Then I have another voltage source over here, and I have another voltage source over here. All right. Now we'll have add resistors. So there is a resistor over here, a resistor over here, and over here. So these are my resistors. Now let me join the circuit. So this is first box or the first loop, okay, and this is the second loop. It's very easy to analyze anything in LT-Spice. This plus will go over here and this negative will go over here. Okay, let me add the values. Here it is 2 volt. Okay, here it is 2 ohm. Then this resistor value is 3 ohm. This is 4 volt. This will be 3 volt. This will be 5 and this will be 4. Got it? Alright, and what is my x and y? This I'll right click and label it as x. So this is my x and this is my y. And actually one node I have need to connect it to ground. So y I will connect it to ground. Alright. So whatever my Vx value will be, that will be my value of Vxy, because Vy is ground now here according to the connections which we have made. So I'll go to simulate, click on run, select DC operating point, click on OK. So here if you see V of X is coming out to be minus 3.7 because Vy is directly connected to ground. So Vxy will be Vx minus Vy. So that will be minus 3.7. So that is correct. And what answer we are getting, what answer we got is also correct. Yeah. So yeah, that's it for this session. Next time we'll explore some more examples using KVL, KCl, and henceforth we'll also solve more numericals on nodal and mesh analysis. So until then, have a good day and thank you.